In this video, we're going to dig into how enzymes speed up the rates of reaction in a more detailed way than we have thus far. It's a super cool topic, and I really look forward to getting into it with you. Now, I really was actually wrestling with how to do this. One of the thoughts I had was, well, why don't I look at a bunch of different enzymatic reactions and sort of try to draw out key themes? And unfortunately, it was just too much. It was too complicated, and I was not doing anything justice. So instead, what I'm going to do in this video is focus in on a particular reaction and try to extract principles from that. That doesn't mean I won't talk about cool reactions in the future. I definitely want to talk about ping pong reactions because who doesn't want to hear about ping pong reactions? But that'll be a future version of me. For the moment, though, in this video, what we're going to say is we're going to ask sort of three things. We're going to say, what do enzymes do generally? We're then going to ask, how does a particular enzyme do its job? And then we're going to zoom back and say, okay, now that we've seen how that enzyme does its job, how does it relate back to those general rules? So that's our approach. So what are our general things that enzymes do? The first is they orient chemical moieties so they're primed to do chemistry, which I'm realizing is a lot of chemistry words, but basically it's lining up all the atoms so the right thing attacks the right other thing, etc. They activate polar atoms by pulling them away from water. So I've said in previous videos that doing things like burying hydrogen bonds or charge away from water, where you don't fulfill it, say a hydrogen bond, you don't fulfill it with another hydrogen bond, or donor or acceptor, it's really unfavorable. Things like that happen in active sites, but that allows this active site to be primed to do interesting chemistry. Let me make myself go away. They stabilize the transition states of reactions. So they find new bonds that basically bind to transition states. And then the other thing that happens in active sites is they're going to do hard chemistry by breaking it into multiple steps. So instead of one single large energy barrier, there's a bunch of small energy barriers that the substrate has to go over on the way to product. Oh, wrong button. So the enzyme we're going to be using to learn how enzymes work in more detail is trypsin. Trypsin is a member of the serine protease family. And hopefully the name protease is making you think, maybe it cuts proteins. In fact, that's what it does. So it binds to amino acid sequences of unfolded proteins, and then it cuts them, particularly after lysine residues. This is present in us right now, breaking down proteins that we consume in our diet. So it's a really important protein. It is also, you might say, a cannibal, right? Because it's a protein that's eating other proteins. So we're studying a cannibal protein today. What's the basic reaction that it does? So trypsin catalyzes peptide bond hydrolysis. So quick reminder that reaction looks something like this. You have nucleophilic attack on the carbonyl. That generates an oxyanion intermediate, and then that oxyanion intermediate resolves by breaking the peptide bond, yielding a broken peptide bond. Quick note about this reaction is that the delta G naught prime for this is less than 0. The reaction is intrinsically favorable, so it will proceed in the hydrolysis direction spontaneously. However, the rate of that reaction is extraordinarily slow. The the uncatalyzed rate of the reaction, is 3 times 10 to the minus 9th per second, so billions of seconds sort of thing. Whereas the catalyzed rate with trypsin or a serine protease in general is 120 times per second. So it gets much, much, much faster, 40 billion times faster when you add the enzyme. This raises the question, okay, we know how much the rate changed. How much does that change, or how much was the change in the activation energy or the transition state energy? So if you watched a previous video of mine, I walked through how to relate these to each other. And if you want to practice, this is a good chance to do so. So you've got some K-cat, you've got K-cat and K-uncat. What was the energy of stabilization required? So maybe you go find a pause button, go do some math, so pause. Assuming you paused, and now we're back, and I'm going to do the math. So the basic relationship is this, that the catalyzed rate over the uncatalyzed rate is given by this ratio. That ratio is related to the difference in the activation energy of the two reactions. You can rearrange this to say the difference in these reaction energies is just minus RT log of the ratio of the rates. So this, I just did some log rules and some division. And what that gives you, if you plug in numbers, is that to get a 40 billion fold speed up, you need to stabilize the transition state by about 60 kilojoules per mole, which according to my rough, I like having this milepost standard, that's about 3 water-water hydrogen bonds to do so of worth of energy. And to be clear, I'm not saying it's 3 hydrogen bonds or exact number of interactions. I'm basically saying it's worth about 3 water hydrogen bonds. That's the amount of energy involved. Okay, so it's speeding up this reaction a lot. How does it do so? And getting into that's pretty complicated in some ways. So what we're going to do is break that into three parts. We're going to ask what's the anatomy of the active site. We're going to do some arrow pushing, and then we're going to do some arrow pushing in a structural context. So let's dig into those. So I'm starting super zoomed all the way in on the active site. I like starting here because it makes the most sense, I guess, to look at the atoms, and then we'll see how it's all put together. This active site has a couple of parts. There's the catalytic triad, which consists of 3 amino acids, an aspartate, a histidine, and a serine. Those have green for their carbons. The aspartate is negatively charged, so it does not have its proton. It's in the carboxylate state. And the serine is going to be the nucleophile in our enzymatic reaction. Now, if you've taken organic chemistry recently, you might be like, what? That's weird. Serine? Maybe I don't remember my amino acids right. But yes, no, you're remembering the right. Serine, the amino acid, is a hydroxyl. Hydroxyls aren't normally aren't nucleophiles in water. A hydroxyl has a pKa in water of about 17. So it has a high proton affinity. But in this active site, we'll see why in a second, the pKa of that is only about 7. So it's a lot better at dropping its proton. It's a lot better at doing chemistry. Now, if you haven't taken organic chemistry for a bit, or you haven't taken it yet, you're like, what just happened? I have no idea what we were talking about it. Don't worry about it exactly, or don't worry about the details of that. The key things to take away right now is we do have a negatively charged aspartate, and that the serine is the thing that's going to do some interesting chemistry. Okay, the catalytic triad is directly adjacent to this thing known as the oxyanion hole. The oxyanion hole is actually built out of backbone amides, and these two in particular are here, and they are unfulfilled hydrogen bond donors, right? So you've got these protons sticking out. They're not interacting with the other parts of the protein, so they're unfulfilled, looking for things to interact with. That's good because it lets them interact with, say, substrate. So this is now our substrate docked in. We've got a substrate carbonyl that can be an acceptor for both of these hydrogen bonds coming off of the proton, coming off of the oxyanion hole. Okay. So we're zoomed way in. Let's start zooming out so that we can understand what in the world's going on. So now what I'm doing is I've just added the rest of the protein and I've wrapped it in kind of, you can think about it like I've wrapped it in saran wrap so we can see the architecture of the protein without getting too bogged down in the details. So protein is now all present wrapped in gray saran wrap. Now we're going to zoom out and see where the active site's situated in that. And hopefully you can see that the architecture looks a lot like what I talked about with enzymes generally. If you watch my general enzymes video, that there's a relatively small active site surrounded by a large rest of the protein, a scaffold to stabilize that active site. I've laid down the substrate here in purple, the whole substrate. So this is a peptide. It's got multiple amino acids, but the active site very carefully positions it so a single peptide bond is there ready to be cleaved. And that puts it in line with this catalytic triad and then the oxyanion hole below it. Okay, I'm going to make one more move to illustrate a couple more points. What I've done is I've taken all of the small spheres representing atoms and I've blown them up to their full scale. So now these are what are known as van der Waals spheres. They're showing how much space these molecules would fill, or these residues. And there's 2 things I want to pull from this. First is it is packed in there, right? There's not a lot of free space. When we draw sort of stick organic chemistry molecules, it can be easy to think, oh, there's room for things. There really aren't, right? These are taking up all kinds of space. There's no extra wiggle room in this pocket. The second thing I want to point out here is down there, hopefully you can see still lurking in there, there's an amino acid. Anybody, well, not anybody, but do you remember at all what the amino acid was that was buried deep in there? Turns out it's an asp and it's negatively charged. And it's pretty weird to take a negative charge and jam it deep inside of a protein, right? And so we're going to be unpacking the consequences of that in subsequent steps here. Okay, so that gave us the anatomy of the active site. Now let's start pushing some arrows to understand what's happening in that active site. So here I'm drawing the active site in a slightly different way than it was structurally, but hopefully identifiably similar. So we've got the catalytic triad here on the top, the oxyanion hole in the bottom. We've got our asp, our his, and our serine. And I've drawn them with these squiggles. That's a pretty standard way in enzymology to say that's just attached to the rest of the protein. Okay. The first event that happens when in this enzymatic reaction is substrate binds. And I showed that in the structure. It binds such that it's putting that carbonyl near the oxyanion hole. Quick notation thing, I'm just drawing this single peptide bond here so we can focus on the chemistry that's happening there. But there is a long N-terminal chain and C-terminal chain hanging off. It's just we're not going to show it because that would be a lot to draw. All right. Now what I'm going to do is I'm just going to move over. So now this is the thing that was on the right is now on the left. So we now have our substrate bound. We can now ask what happens to get this peptide bond cleaved. So the first thing that's going to happen is this negatively charged aspartate is going to grab onto a proton from the histidine. The reason it's going to do that is because this thing really is unhappy, right? We've got a negative charge on this aspartate that is unfulfilled. So what is it going to do? What's an aspartate going to do? It's going to steal a proton from wherever it can get it, and it's going to steal it from the histidine. When it steals it from the histidine lone pair, now it's short a proton, so it's going to grab a proton off of the serine. And that is going to give a negative charge or make the serine ready for its own attack. Now, a quick sort of caveat on this is I'm drawing this in sort of this formal negative charge kind of way. It's actually probable based on a bunch of careful crystallographic work and quantum mechanical calculations that this is actually kind of a shared hydrogen. There's not really it's not really hydrogens flipping back and forth. It's sort of the shared between aspartate and histidine. People call it a low barrier hydrogen bond, but ultimately the effect of that is the same in that it makes the lone pairs of the nitrogen on the histidine have a high affinity for the proton on the serine. So the effect is that it's going to basically make that into a nucleophile. But this is a simplified way to draw it. The other thing I should mention here is if you want to that's if you want to make it more complicated. If you want to make it less complicated, you want to just mental image for what's going on here, which isn't exactly right, but it's good enough to understand conceptually what's happening. You can think about the aspartate is desperate for a proton, so it yanks the proton. And then in tug-of-war fashion, then the histidine is short of proton, so it's going to yank the proton off of the serine. So you can think about this as a tug-of-war where the aspartate through the histidine to the serine pulls the proton off of the serine. Okay, so catalytic triad has now primed our serine to do nucleophilic attack. What's the next step in our reaction? We're going to C attack. This is going to attack the carbonyl, generate an oxyanion intermediate. This is a tetrahedral intermediate that can form all kinds of favorable interactions with that oxyanion hole. So forming this thing is the rate limiting step of the reaction. It's the chemically wacky state. When I talked about Arrhenius relationships, this is the thing that's just a low probability thing you're just waiting to have happen. Now you've stabilized it with the oxyanion hole, so it happens a lot more often. All right, you are now in this state where you've got your oxyanion in the oxyanion hole. We're now going to cleave the peptide bond, so the electrons are going to come down here and reform the double bond. You now have two possible options. You could break the bond to the serine, or you could break the peptide bond. Actually, both happen with some frequency, but if this is sitting long enough in the active site, eventually this is going to happen. It's going to break that bond, and it's going to grab onto the proton off of the histidine, yielding the following. And then the histidine, I forgot a step, it's going to pull the proton off of the aspartate. What you're left with then is you've kind of put this part of the catalytic triad back to where it started. You've cleaved the peptide bond, and now you've got the N-terminal part of the peptide still stuck on the serine. So we've covalently attached the peptide to our trypsin. Next thing that happens is this is going to diffuse out of the active site, and water is going to diffuse in. I said it was packed and crowded, but now you've taken a big chunk of peptide out, right? So now there's enough room for water to get in. What that water allows is for yet another nucleophilic attack. So basically, the catalytic triad is still up and doing its business. That aspartate is still unfulfilled. It still wants a proton from somewhere. Grabs onto the proton from the histidine. The lone pair on the histidine grabs the proton off of the water, and that turns this into a good nucleophile, which then creates a new tetrahedral intermediate, and it does so using water now, right? So now we brought this water hydroxyl in. We are so close to being done because the next step is we're going to resolve that carbonyl. And when that happens, rather than breaking the newly formed bond with water, we're going to actually break the bond to serine, which is going to lead to the restoration of the catalytic triad to its starting point, right? Now we've got the asp, we've got the his, we've got the serine, and they're all back to where they started, and our peptide bond is no longer covalently attached to the active site. So the final step is that is going to leave the pocket, giving us back our active site. So this is in fact a catalyst. It did the chemistry, but it was not consumed or destroyed in the chemical reaction. Okay, so let's summarize. There was a lot of details now, but summarize the key bits. The first is the binding pocket has positioned the peptide bond to be cleaved in the active site, right? It was lined up so the nucleophilic attack would happen from that serine onto that particular peptide bond. The whole catalytic triad business, particularly that negatively charged aspartate pulled away from water, is going to turn the serine into a good a nucleophile, and then it actually turns a water molecule into a good nucleophile, right? By ripping off its proton because that histidine is in an unhappy proton sharing relationship with an aspartate. And then finally, the oxyanion hole's job here is to stabilize the oxyanion intermediate. So with these three things all lined up, we end up with an enzyme that can increase the rate of this reaction by 40 billion fold. Okay, so we've done the anatomy of the active site, we've done the arrow pushing mechanism. Now I'm trying something new. I'm going to try to put it into a structural context. That's for me is what I've noticed in the past is students have struggled the most with, okay, I saw arrow pushing, how does that translate into a protein structure? So we're going to attempt to do that. And the way that we're going to do that is I'm going to attempt to scribble on this as we go through the steps. Quick caveat, I'm going to show protons and stuff moving around here. I'm just trying to mimic the formal arrow pushing mechanism. These were not generated with quantum mechanical calculations. They are an artist's rendition, a wild fantasy, but hopefully they give us a notion for how the bonds are flowing in sort of across this reaction, even if I would not hang my hat on this is exactly how the protons work. This is their geometry, this is their bond length or anything. This was derived from a crystal structure of trypsin bound to an inhibitor. So it's at least there's some basis for reality there. Okay, so quick reminder of what's going on here in this active site. We've got our catalytic triad, which is the aspartate, the serine, and the aspartate, histidine, and serine that are in this basic orientation, directly adjacent to this oxyanion hole with its unfulfilled hydrogen bond donors. What we're going to do is just start rolling through the reaction, and I'm going to narrate as we go. So here we've got the enzyme alone. Substrate docks and forms interactions with the oxyanion hole. Over here in the catalytic triad, the aspartate pulls a proton off the histidine, which pulls a proton off of the serine. That is now a nucleophile that can do a nucleophilic attack on the carbonyl. That generates a tetrahedral intermediate, which is stabilized by this form here. By the oxyanion hole, and then we break the peptide. I gotta stop. We're going too fast here. My brain's not working. Okay, so let's go back. Apparently I can't go back the way I wanted to. Okay, so we cleaved the peptide bond there. Once we've cleaved the peptide bond, there we go. We're going to restore the catalytic triad back to its starting point, and now we're at the halfway point of the reaction. The first cleavage product just left, and now we bring in the water. This water is going to be primed by the catalytic triad, just like the serine was, to become a nucleophile. So we're moving the protons off the side there. It's going to do a nucleophilic attack on the carbonyl, which is going to then be stabilized. The intermediate is going to be stabilized with the oxyanion hole. But now we're going to break this bond on resolution. We've separated the peptide now, it's no longer covalently bound to the rest of the pocket. We now restore the catalytic triad to its starting state. And now the substrate can leave and we are back at the beginning. Okay, that might be worth watching a couple of times through. Sorry, that's a lot to follow and go through. But I think the thing I mainly want to have you take away is that this really is a motion of these protons. It really is a physically connected array of, you can think about it as pushing and pulling, even if it's not exactly right, but still it's sort of a linear array. And then also this critical rule here that when this is forming oxyanions, these hydrogen bonds are specifically in an orientation where they can form great hydrogen bonds to stabilize it. Okay, we're almost done here. Do want to come back though and said, we just did a whole bunch of stuff about a particular enzyme. What does this tell us about how enzymes work as a group? So I said that enzymes orient chemical moieties so they're primed to do chemistry. We see that in the catalytic triad because the catalytic triad is lined up precisely with that peptide bond so that serine can do its nucleophilic attack, right? The whole protein architecture is designed to put that protein into that orientation, or the substrate into that orientation. We see the activation of polar atoms by pulling them away from water. Maybe most importantly here, this aspartate is buried. But what that does is, again, because there's not a bunch of water around, it allows that aspartate to make serine into a nucleophile bridged by the histidine. So these atoms, because those charges aren't fulfilled inside the center of the protein, they want to go on and do interesting chemistry. Enzymes stabilize transition states. In this case, we see that through this oxyanion hole. It binds to that oxyanion tetrahedral intermediate and makes it more stable. And then they do hard chemistry by breaking it into multiple steps, right? This, instead of being one single reaction, there's actually two attacks, right? You first have the attack with the serine, followed by the attack with the water. So we're breaking this into multiple steps rather than one big step. Okay, so hopefully after that, you have a better understanding of what it means mechanistically for an enzyme to speed up a reaction. And hopefully now you know something about how these classes of proteins, as trypsin or serine proteases, work. From here on out, we're going to talk about things like Michaelis-Menten kinetics. Looking forward to getting into that with you. But until then, have a great time of day that you're having.